I'm going to ask you again tomorrow. I don't want any blank stares. So let's talk about a standing wave. So here is, let's get some color involved. This is red. Yeah. Here is a wave. What kind of wave is that? Transverse. There you go. This is a transverse wave. The particles move from particular to energy in the wave. Now, let's compare this to our slinky lab outside. The slinky lab fixed or descent? Fixed. Very good. So it's going to bounce back how? Inverted. So this is another wave to come back like this. Like that. And this is going to tell us that this would be somewhere around the middle there, would be our equilibrium line. So, if we're looking at a slinky, so we're going to send a bunch of pulses one after another, and they go up and down and back and forth. So now, not only is there one, so we're going to do this quickly now, not only is there a pulse going forward, at the same time that's going forward, there's going to be a second pulse going backwards at the same time. And that's when we get this kind of standing wave here. What would we expect would happen? What would we expect to happen right here? What will we see at those points right there? We actually see no energy at all. And this is the point where each wave, either going forward, the graph's going forward, or going backwards, whether it's going forward or backward, that's the point where the wave's at a zero equilibrium or zero amplitude, I guess you would say. And so when those cross, you're going to take basically 0 plus 0 and still get back out at 0. There's going to be points that develop right there that have no motion at all, and we call those points nodes. Remember that there's no motion, so we call it a node dip.
So that's only standing wave?
Well, I mean, I guess they technically occur in a pulse. Well, I guess, yeah, only standing wave. Both kinds have them, but it's tougher to see than the longitudinal.
Okay.
Because you can't really, longitudinal is like sound and kind of like water, but.
I'm very well understand. I was thinking transverse.
Oh, this is a you said before, transverse wave. Yeah. But everything we say could happen also in a longitudinal wave, it's just harder to explain. So, to go back over to our little game over here, we can do the same thing. They oscillate this, and then bounce back. That's not really that over there. Now there's points here where you kind of see it happen too. One wave's going down, now it hits, bounces back, and now it's getting bigger as it goes back. There's points where there's no motion, that's these green dots, so to speak. Those are our nodes going on here. And between those nodes, there is motion. I think the computer puts them there on purpose because of the nodes. If they start that way, or maybe that's not, I don't know, that's why they just show up there. Yeah, it keeps getting kind of bigger and bigger and bigger. So I'll go back to ours. It just gets kind of ridiculous after a while. So these are our nodes. The green dots in this case are our nodes. Now the other places, now you have these waves, you would think they might cancel out. What's actually happening is because they're being sent at a certain frequency, you get these points where the incoming wave also meets up with the outgoing wave, and they kind of actually add together at that point there because the reflected wave can add with it there. And so what do you think we call these points in here? We call these antinodes. Very creative naming as a part of our physicists. And so the points where there's, like, these are the points we would say there's maybe destructive interference, we get adding down to 0. The points where there's constructive interference, we get large crests in there, and that's what we're calling antinode. So node where no motion, antinode where there's the maximum motion. As that's happening over here, watch it. Let's slow this down a little bit. So here's our first pulse coming down. Now it's about to reflect. So we're going to start seeing now particles coming back out like this. We have another wave on its way out. So now, because you have the one trying to reflect up, but also the second one kind of coming behind it, this is going to, all of a sudden, these particles here are going to be zero for a moment, because they're bouncing, they're adding together with it down and up at the same time. But then that meets up with the other part of the up coming in, and you have big old thing on top of it, and that process keeps happening. You get this standing type wave, and then it gets kind of weird. It gets weird because of the if we figured out, if we did the math for it, we knew how long this distance was, and we set up the frequency and such that this oscillated at the right frequency to produce like one wavelength that fit into this distance, then it would work out, it would be nice and pretty for us. We're going to do that math for right now. But we're setting out like something, if this was, say, well, we can see this is 90 centimeters long, give or take, and we're setting out wavelengths that are like 60 centimeters long, so it's not lining up perfectly, so we get these weird, like at the end we get these like weird results that start going crazy. And stuff like that. And so if we set it up, I mean, we could maybe guess. Let's go back to our notes really fast here. What do I call the distance from crest to crest of the same wave? Wavelength, that we're going to get with lambda. So the height of this thing, the amplitude, like that. And so you can see if you basically you can shift it over if you go like 1, 2, 3 nodes like that, or if you span 2 nodes, like also say there's one wavelength. So we can look at that. So we're going to try to make some scanning waves with this device here. This is called